Imagine standing on the surface of Venus. Within seconds, the 900-degree heat would vaporize your body. The crushing atmospheric pressure 92 times stronger than Earth's would compress your remains into nothing. Clouds of sulfuric acid would rain down from above, though they'd never reach the ground before evaporating in the Inferno below. Now imagine this. Walking across that same planet 200 years from now, breathing fresh air, watching blue oceans shimmer under a protective atmosphere. No spacesuit, no habitat dome. Just you and humanity's greatest achievement, a second Earth. This isn't science fiction. This is the plan. Venus wasn't always hell. Scientists believe that billions of years ago, Venus might have been remarkably Earth-like with liquid water oceans, moderate temperatures, and maybe even the conditions for life to emerge. But something went catastrophically wrong. A runaway greenhouse effect transformed our planetary twin into the most hostile world in the inner solar system. Here's what makes Venus such a nightmare. Its atmosphere is 96% carbon dioxide, creating a greenhouse effect so powerful that the surface temperature reaches 864 degrees Fahrenheit hot enough to melt lead. The atmospheric pressure at ground level equals what you'd experience half a mile underwater on Earth. And those famous clouds? They're not water vapor. They're concentrated sulfuric acid, ranging from 70 to 98% concentration, depending on altitude. But here's the thing that keeps scientists awake at night. Venus is Earth's twin in almost every other way. It's nearly identical in size and mass, with about 90% of Earth's surface gravity. It's in our solar neighborhood, just next door, cosmically speaking. And unlike Mars, which has lost most of its atmosphere, Venus has plenty of raw materials to work with. The question isn't whether Venus could be transformed. It's how. Let's talk about why Venus matters more than you think. While everyone's obsessed with Mars, Venus actually has some serious advantages. Mars is cold, has barely any atmosphere, and only 38% of Earth's gravity, which means if you live there long-term, your bones and muscles will deteriorate. Venus? Full Earth-like gravity, rich atmosphere, and it's closer to Earth, meaning shorter travel times and better communication windows. The real breakthrough in our thinking about Venus came when researchers at MIT discovered something remarkable in 2023. They found that the basic building blocks of life nucleic acid bases that make up DNA can actually remain stable in concentrated sulfuric acid. This turned conventional wisdom on its head. We'd always assumed Venus's acid clouds made any form of complex chemistry impossible. Turns out we were wrong. But the surface? That's another story entirely. At 900 degrees Fahrenheit, no known material can survive unprotected for long. The Soviet Venera probes that landed on Venus in the 1970s and 80s only lasted about 2 hours before being destroyed, and those were heavily armored spacecraft designed specifically for that environment. The longest any probe has survived on Venus's surface is just 127 minutes. That's the benchmark we're working against. The pressure is equally staggering. 92 bars of pressure means the atmosphere at Venus's surface is as dense as water. It's not really a gas anymore. At those temperatures and pressures, carbon dioxide becomes what scientists call a supercritical fluid. It has properties of both a gas and a liquid, which creates bizarre weather patterns and makes the engineering challenges even more complex. And then there's the rotation problem. Venus rotates once every 243 Earth days, and it rotates backward compared to most planets. This means a single day on Venus is longer than a year on Venus. If you stood on the surface, you'd experience about 58 Earth days of continuous sunlight, followed by 58 Earth days of darkness. That's not exactly ideal for growing crops or maintaining circadian rhythms. Before we terraform the entire planet, there's a genius intermediate step: floating cities in the clouds. I know it sounds like something out of Star Wars, but the physics actually work and work beautifully. Here's the remarkable thing. At an altitude of about 50 kilometers above Venus's surface, the conditions are the most Earth-like in the entire solar system. The temperature hovers between 0 and 50 degrees Celsius. The atmospheric pressure is roughly 1 bar, exactly what we experience on Earth's surface. Yes, you're still surrounded by carbon dioxide and sulfuric acid clouds, but you're not being crushed or incinerated. NASA scientist Jeffrey Landis proposed something elegant, a breathable mixture of nitrogen and oxygen. The air we breathe would actually be a lifting gas in Venus's atmosphere. It's lighter than the surrounding carbon dioxide, which means a balloon filled with Earth-normal air would float. You could create entire cities supported by nothing more than breathable atmosphere inside a protective shell. Think about that for a second. On Earth, we need helium, or hot air, to float. On Venus, the air we breathe is the helium. Your habitat's life support system doubles as its flotation device. It's the ultimate 2-for-1 deal. These cloud cities could be constructed from materials harvested directly from Venus's atmosphere. Carbon nanotubes and graphene super-strong materials that are among the strongest substances known to science can be manufactured from the carbon dioxide that makes up most of Venus's atmosphere. You literally build your colony from the air around you. No need to ship construction materials from Earth at astronomical cost. The proposal gets even more interesting. These floating platforms could do double duty as terraforming stations. While providing living space for early colonists, they could also house atmospheric processing equipment. Giant chemical factories in the sky, gradually converting Venus's hostile atmosphere into something more breathable, one molecule at a time. Each city would need to be protected from the sulfuric acid clouds, likely using acid-resistant polymers or ceramic coatings. But here's a surprising fact. At the cloud level, the sulfuric acid isn't as concentrated as it is lower down. At 50 kilometers, it's about 75% concentration, still deadly if you're exposed to it, but manageable with proper materials science. These cities could be enormous. Dr. Alex Howe from Princeton calculated in his 2022 research that artificial surfaces floating at Venus's cloud level could span thousands of square kilometers. They'd use nitrogen, which would be separated from Venus's atmosphere as the primary lifting gas for the structure itself, with breathable air providing additional lift for habitats. The genius of this approach is that it's scalable and immediate. You don't need to wait 2 centuries for the planet to cool down. You could potentially start building these within a few decades, once we have the manufacturing capabilities in space. They'd provide a base of operations for the longer, more ambitious terraforming project below. Now we get to the big show, the plan to actually transform Venus itself. And it starts with something that sounds absurdly simple. Put Venus in the shade. British scientist Paul Birch proposed the most detailed version of this in 1991, and it remains the foundation for most serious terraforming proposals. The concept is called a solar shade, essentially a giant mirror positioned between Venus and the Sun that blocks sunlight from reaching the planet. The scale is almost incomprehensible. We're talking about a structure that would need to be about 4 times Venus's diameter if positioned at the L1 Lagrange point, the gravitationally stable spot between Venus and the Sun. That's roughly 48,000 kilometers across. For context, that's about 4 times the diameter of Earth. It would be the largest structure ever built by humanity, by several orders of magnitude. But here's where it gets clever. You wouldn't build one solid mirror. Instead, you'd create a slatted system, multiple panels angled at about 30 degrees. Each panel reflects light to the next panel, which redirects it away from Venus. This solves a critical problem: solar radiation pressure. A flat mirror would act like a solar sail, and the pressure from reflected sunlight would push it out of position. The angled slats redirect that pressure, essentially allowing the structure to balance itself. The material wouldn't be thick metal or glass. It would need to be incredibly thin, think aluminum foil, or even thinner, coated with a reflective layer. We're talking nanoscale thickness in some designs. Even so, the total mass required would be enormous, likely hundreds of millions of tons of material. That material would need to be manufactured in space, probably using resources from the Moon, asteroids, or even Venus itself. Once the shade is in place, Venus would begin to cool. And this is where thermodynamics becomes our friend. Venus receives about twice the sunlight Earth does, which is what drove its runaway greenhouse effect in the first place. Cut off that sunlight, and the planet can finally start radiating away its excess heat into space. The timeline, according to Birch's calculations, would be about 60 years for Venus to cool down to the critical temperature, 31 degrees Celsius. That's when something extraordinary happens. The carbon dioxide in the atmosphere reaches its critical point at the existing pressure. Below this temperature, the CO2 begins to liquefy. Picture this. After 6 decades of darkness, Venus begins to rain. Not water, rain, carbon dioxide rain. The sky starts dripping liquid CO2, which falls to the surface and pools into rivers and seas of liquefied greenhouse gas. This would be one of the most spectacular weather events in the solar system, a planet-wide rainstorm that lasts for decades. As cooling continues, temperatures would drop below negative 56 degrees Celsius, and the liquid CO2 would freeze into dry ice. Venus's surface would become covered in a thick blanket of frozen carbon dioxide, potentially hundreds of meters deep in some places. The atmospheric pressure would plummet from 92 bars to perhaps 3 or 4 bars, still higher than Earth's, but approaching manageable levels. This frozen CO2 represents both an opportunity and a challenge. It contains about 500 quintillion kilograms of carbon that needs to be dealt with. You can't just melt it back into the atmosphere. That would undo all your work. Several proposals exist for handling it. Option 1. Sequester it underground. Venus likely has caverns and geological formations that could store compressed CO2 permanently. You'd need to prevent it from sublimating back into the atmosphere, which means keeping it pressurized and cold. This is technically possible, but would require extensive robotic mining operations. Option 2, and this is where it gets really interesting. Export it to Mars. Mars needs more greenhouse gases to warm up and thicken its atmosphere. Venus has too much. It's the ultimate interplanetary recycling program. You'd use solar-powered mass drivers or space elevators to launch chunks of dry ice into space, where they'd be captured and sent to Mars. The graphite byproduct from other processes could go two-spreaded on Mars's polar ice caps, and it would absorb sunlight, helping to melt them and release more CO2. But there's a problem with the solar shade approach that keeps engineers up at night. Stability. Maintaining a structure 48,000 kilometers across at a fixed point in space requires constant adjustments. Solar radiation pressure, gravitational perturbations from other planets, even the slight drift from manufacturing imperfections, all of these would cause the shade to shift position. You'd need potentially millions of small thrusters, positioned about every kilometer across the structure, making constant micro-adjustments. The control system for such a structure would be staggeringly complex. Some scientists have proposed alternatives. Instead of one massive shade, create a swarm of smaller reflectors, millions of them, that collectively block enough light. Each would be easier to manage individually, and if some fail, the system continues working. Others suggest using electromagnetic fields or even exploiting the solar wind itself to maintain position. Cooling Venus is only half the battle. We still need to deal with all that carbon dioxide in the atmosphere, and we need to add water, which Venus has almost none of. This is where another bold proposal comes in, originally suggested by scientist Paul Birch. Bombard Venus's atmosphere with hydrogen. Lots of hydrogen, and I mean lots. The chemistry is actually straightforward. When hydrogen reacts with carbon dioxide in the presence of heat and catalysts, you get several possible products. One major reaction pathway produces water vapor and carbon monoxide. Another produces water and graphite pure carbon in solid form. The exact mix depends on temperature, pressure, and what catalysts are present. The proposed approach would involve importing hydrogen from the outer solar system. Saturn's moons, particularly Enceladus and Titan, are rich in water ice. Jupiter's moon Europa has even more. You'd essentially be mining ice, converting it to hydrogen and oxygen, and shipping the hydrogen to Venus. The scale is staggering. You'd need to deliver millions of tons of hydrogen to convert enough of Venus's CO2. But here's where it gets ingenious. Once you start getting water vapor in Venus's atmosphere, you can begin a chemical cascade. Water molecules can be split by ultraviolet light from the sun, a process called photodissociation producing hydrogen and oxygen. That hydrogen can react with more CO2. It's a chain reaction that, once started, could become partly self-sustaining. The graphite byproduct from these reactions would rain down onto the surface, potentially hundreds of meters of pure carbon dust covering the planet. This is actually useful. Graphite is an excellent material for manufacturing. You can make carbon nanotubes, graphene, industrial diamonds, and countless other materials from it. Venus would essentially develop a ready-made construction materials economy. The oxygen produced from these reactions is both good and bad news. Good news: we need oxygen for a breathable atmosphere. Bad news: too much oxygen is also a problem. Pure oxygen at high pressure is incredibly reactive and dangerous. You'd need to carefully control the reaction rates and timescales to avoid creating an oxygen-rich atmosphere that would literally cause the graphite on the surface to spontaneously combust, converting back into CO2 and undoing all your work. Some proposals suggest introducing iron aerosol into the atmosphere as a catalyst and to help manage the oxygen. Iron oxide can be produced, which would fall out of the atmosphere as rust-colored dust. Mars red dust on Venus. There's a certain poetic irony to that. The iron could be sourced from metallic asteroids, which are relatively common in the inner solar system. An alternative proposal from Mark Bullock and David Grinspoon focuses on a different chemical pathway, introducing calcium and magnesium compounds into the atmosphere. These would react with CO2 to form carbonates-stable minerals that lock carbon away in rock form. This is actually how Earth sequesters most of its carbon in limestone and other carbonate rocks. Venus might have had similar processes early in its history, but the runaway greenhouse effect overloaded the system. The advantage of the carbonate approach is that it's potentially more stable long-term. Once carbon is locked into carbonate minerals, it's not easily released back into the atmosphere. The challenge is delivering enough calcium and magnesium to process 500 quintillion kilograms of CO2. You'd need to mine asteroids, possibly even redirect small asteroids to impact Venus, delivering their mineral payloads directly. Even after you've dealt with the CO2, Venus has another glaring problem. It's bone dry. The entire planet has about 100,000th the amount of water that Earth has. For comparison, all the water in Venus's atmosphere would be enough to cover the surface to a depth of about 3 centimeters. Earth's oceans average about 4 kilometers deep. Venus lost its water through a process called hydrodynamic escape. Billions of years ago, when Venus was hotter but still had water, the heat caused water molecules to rise high into the atmosphere. Solar ultraviolet radiation split those water molecules into hydrogen and oxygen. Hydrogen is so light that it escaped Venus's gravity and drifted off into space. Over millions of years, Venus lost its oceans one molecule at a time. To terraform Venus, you'd need to replace that water. Several proposals exist for how to do this. The most commonly discussed approach is redirecting water-rich comets or asteroids. Saturn's moon Enceladus is essentially a giant ice ball with a liquid ocean beneath an icy crust. It's estimated to contain more water than Lake Superior. Redirect Enceladus or a similar moon toward Venus, and you could deliver vast quantities of water in one massive impact. But there's a problem. At Venus's current temperature, any water you add would immediately evaporate and potentially restart the greenhouse effect you just spent a century stopping. You'd need to deliver water during or after the cooling phase, when surface temperatures have dropped to reasonable levels. Another approach. Once the CO2 atmosphere is converted using hydrogen, you'd get water vapor as a byproduct. Some calculations suggest this could produce enough water to create shallow seas covering portions of the surface. It wouldn't be Earth-like oceans, maybe more like Mars once had, with shallow seas and large land masses. But it would be a start. There's also the possibility of mining what's called hydrated minerals in Venus's crust. Some scientists believe Venus might have water locked up in its rocks, similar to how Earth has vast quantities of water in its mantle. Heating these rocks and extracting the water would be an enormous industrial operation, but it could provide a local source rather than importing everything from the outer solar system. The challenge with any water delivery method is controlling the amount. Too little water, and Venus remains a desert world. Too much water, and you could create a planet-wide ocean with no land interesting, but not what we're aiming for. Earth's ratio of about 70% ocean to 30% land seems to work well for habitability and climate stability. Remember Venus's bizarre rotation? One Venus day equals 243 Earth days, and it rotates backward. This creates those extreme day-night cycles I mentioned earlier. 58 Earth days of sunlight followed by 58 Earth days of darkness. Surprisingly, some scientists argue this might not be as big a problem as you'd think. Dr. Alex Howe's research suggests that a terraformed Venus with its current slow rotation would have a climate similar to Alaska or Siberia, with an extended summer-like day period featuring warm temperatures, heavy cloud cover, and abundant rainfall, followed by a winter-like night period with cold temperatures and snow. Plants and animals could potentially adapt to this cycle. Deep-rooted plants could store energy during the long day to survive the long night. Animal species could hibernate or migrate, following the day-night terminator around the planet. It would be weird and alien, but not necessarily uninhabitable. However, if we decided we really wanted to speed up Venus's rotation, we'd need to apply enormous amounts of energy. Physicist Paul Birch calculated that accelerating Venus to an Earth-like 24-hour day would require about 1.6 x 10^29 joules of energy. For context, that's about 1 billion times more energy than all of humanity currently produces in a year. One theoretical method would be to use carefully choreographed flybys of large asteroids or comets. The gravitational interaction could transfer angular momentum to Venus, gradually speeding up its rotation. You'd need multiple objects, each at least 100 kilometers in diameter, passing very close to Venus at precise angles and velocities. The engineering challenges are immense. One miscalculation, and you're not speeding up the planet, you're causing an extinction-level impact. An alternative approach: use the atmosphere itself as a massive momentum transfer system. Mass drivers on the surface could launch material into space at high velocity in a direction that would gradually accelerate the planet's rotation. Over thousands of years, you could potentially speed up Venus this way, but it would require so much infrastructure and so much time that most scientists consider it impractical. The consensus seems to be, live with the slow rotation, at least initially. Use orbital mirrors in the atmosphere to provide supplemental lighting during the long night and shade during parts of the long day. Paul Birch proposed a rotating Soletta mirror in polar orbit that would create artificial day-night cycles, reflecting sunlight to the dark side of the planet and providing shade to the bright side. Here's a problem that's easy to overlook but potentially catastrophic. Venus has no magnetic field. Earth's magnetic field generated by our rotating liquid iron core creates a protective bubble called the magnetosphere that deflects the solar wind. Without it, high-energy particles from the sun would strip away our atmosphere and bombard the surface with dangerous radiation. Venus's atmosphere is so thick that it provides some radiation protection through sheer mass, But once you thin out that atmosphere during terraforming, you've got a problem. The solar wind would start eroding your new atmosphere, undoing centuries of work. Over millions of years, Venus could lose its atmosphere again, just like Mars did. Several solutions have been proposed. One comes from Japanese scientists at the National Institute for Fusion Science. They suggest building a series of superconducting rings at various latitudes around Venus. Each ring would carry enormous direct currents, generating powerful magnetic fields. Together, these would create an artificial magnetosphere that could deflect the solar wind. The system would need to operate continuously and would require enormous amounts of power. Fortunately, Venus gets plenty of sunlight for solar power. The superconducting rings would need to be kept cold, which is actually easier in space than you'd think. Radiators can dump heat very effectively into the cold vacuum of space. An intriguing side benefit: this system could also serve as a planet-wide energy storage and transmission network. Superconducting cables can transport electricity with zero loss, so you could generate power anywhere on the planet and transmit it anywhere else. It's the ultimate smart grid. Another proposal, published in scientific journals, suggests positioning a magnetic dipole shield at the L1 Lagrange point, the same location as the solar shade. This would be a powerful electromagnet that creates a magnetic field large enough to deflect the solar wind before it reaches Venus. The advantage is you don't need to wrap the entire planet in superconducting cables. The disadvantage is maintaining a massive electromagnetic device at L1 along with everything else you're putting there. There's also a more exotic possibility: restart Venus's core. Earth's magnetic field is generated by convection in our liquid iron outer core. Venus likely has a similar iron core, but it's not generating a field, possibly because Venus's lack of rotation reduces the dynamo effect. If you could heat Venus's core or increase its rotation, you might kickstart a natural magnetic field. But this is far beyond our current capabilities. We can't even directly access Earth's core, let alone manipulate Venus's. Let's talk about the elephant in the room. How long would all this take, and what would it cost? Dr. Alex Howe's 2022 research on floating artificial surfaces in Venus's clouds estimated that a complete terraforming project could be completed in a minimum of 200 years in a best-case scenario. That's if everything goes right. If we have the technology ready, if the funding continues uninterrupted for 2 centuries, and if we don't encounter unexpected problems. A more realistic estimate might be 300–500 years. The cost? Impossible to calculate in today's dollars, but we can look at the scale of resources needed. The solar shade alone would require hundreds of millions of tons of material likely manufactured from lunar regolith, asteroid metals, or carbon from Venus's atmosphere. We'd need to establish industrial operations throughout the inner solar system. The hydrogen required for atmospheric conversion would need to come from the outer solar system. Each mission to Saturn's moons and back would take years, even with advanced propulsion systems. You'd need a continuous stream of cargo vessels, possibly hundreds or thousands of them operating simultaneously over decades. For perspective, the International Space Station, humanity's largest off-world structure, has a mass of about 420 tons and cost over $150 billion to build. The solar shade for Venus would be roughly 1,000,000 times more massive. Even accounting for reduced costs as space infrastructure improves, we're talking about the largest construction project in human history by several orders of magnitude. But here's where it gets interesting. The project could potentially pay for itself. Those floating cities in Venus's clouds could become economically productive long before the surface is ready for habitation. Manufacturing using Venus's abundant carbon and solar energy, hosting scientific research facilities, even tourism for the extremely wealthy adventurous types. The graphite produced from atmospheric conversion is valuable. Carbon nanotubes and graphene are among the most valuable materials by weight in existence. If you're producing millions of tons of pure carbon as a byproduct of terraforming, you've got an instant export economy. And there's a philosophical argument. What's the cost of having a second Earth? A backup for humanity if something goes wrong with Earth 1. The ability to support trillions of humans instead of billions? From that perspective, almost any cost seems justified. The project would require international cooperation on an unprecedented scale. No single nation could fund this. It would need to be a multi-generational commitment from humanity as a whole. Treaties would need to be established. Who owns Venus? Who controls the terraforming equipment? How do you ensure the project continues across changes in government and economic conditions? There's also the question of priority. Should we terraform Venus or focus on Mars? Mars is often considered the easier target. It's already cold, so you don't need to cool it down. But Mars has challenges Venus doesn't. Weak gravity, no magnetic field, and not enough atmosphere to work with. Venus has the right gravity and plenty of raw materials. It's just too hot and hostile. Some scientists argue we should do both simultaneously, using Venus's excess carbon dioxide to warm Mars. Before we get too excited about remaking an entire planet, we should probably ask, should we? The most immediate concern. What if Venus has life? We've found evidence that nucleic acid bases, the building blocks of genetics, can survive in sulfuric acid. Some scientists have proposed that life might exist in Venus's clouds, possibly adapted to conditions that would be instantly lethal to Earth life. The 2020 phosphine detection in Venus's atmosphere sparked enormous controversy. Phosphine on Earth is primarily produced by life, so its presence on Venus could indicate biological activity. Later analysis suggested the phosphine detection might have been a measurement error, but the possibility remains open. If Venus does harbor life, even microbial life, terraforming would be genocide on a planetary scale. There's also the argument about natural preservation. Venus is a window into planetary evolution, a natural laboratory showing us what happens when greenhouse effects run out of control. Transforming Venus would destroy that scientific opportunity forever. We can never unring that bell. Some ethicists argue that we should explore and study Venus thoroughly before deciding to terraform it. Maybe decades of research, even a century or two of science missions. Learn everything we can first. Others counter that humanity might not survive centuries of climate change and overpopulation on Earth. We need a backup now, not later. There's also the question of unintended consequences. Earth's biosphere has been evolving together for billions of years. Countless feedback loops and relationships between species, atmosphere, and geology maintain stability. We don't fully understand all these connections even on our home planet. What happens when we try to create a biosphere from scratch on Venus? What if we trigger unexpected chemical reactions, or create unstable climate feedback loops, or introduce Earth organisms that evolve in unpredictable ways? Some scientists propose a middle path. Create habitats in Venus's clouds, but leave the surface alone, at least for now. This provides living space and economic opportunity while preserving Venus's natural state for study. We could learn from Venus for centuries before deciding whether to transform it. Venus represents perhaps the ultimate challenge in planetary engineering. It's simultaneously the most Earth-like planet in the solar system and the most hostile to human life. Transforming it from a sulfuric acid hell into a second Earth would be humanity's greatest achievement, or its greatest folly. The plans we've discussed aren't science fiction. They're based on real physics, real chemistry, and real proposals from respected scientists. The technology doesn't fully exist yet, but nothing in these plans violates the laws of physics. It's engineering, not fantasy. Dr. Ramses Ramirez from the University of Central Florida, who studies planetary habitability, puts it this way: terraforming research isn't just about living on other worlds. It's about understanding planetary systems, climate dynamics, and the boundaries of what's habitable. That knowledge could help us protect Earth from our own runaway greenhouse effect. The floating cities in Venus's clouds could potentially be built within this century. They'd provide humanity with experience in off-world living, in managing closed-loop life support systems, in adapting to alien environments. They'd be the proving ground for the longer terraforming project below, the full surface transformation. The solar shades, the atmospheric conversion, the water delivery would take centuries. It would be a multi-generational project unlike anything humanity has attempted. The people who start the project would never walk on a terraformed Venus. Neither would their children or their grandchildren. It would require a commitment to a future we can barely imagine. But consider what's at stake. Venus offers 90% of Earth's surface area with full Earth-like gravity. It's a potential home for billions of humans. It could be covered with cities, forests, oceans, farms, a thriving biosphere just 40 million kilometers from Earth at its closest approach. The technology to begin this process. The floating platforms, the atmospheric processing systems, the space-based construction capabilities would also advance our abilities here on Earth. Better materials, science, better energy systems, better understanding of climate and atmospheric chemistry. The spin-off benefits could be revolutionary. Maybe in 300 years, humans will stand on the shores of a Venusian ocean and look up at a blue sky, watching Earth rise as a morning star. They'll breathe air that was once carbon dioxide and sulfuric acid clouds. They'll walk on land that was once hot enough to melt lead. And they'll know that humans did this, that we took the most inhospitable world in the inner solar system and made it home. The question isn't really whether we can terraform Venus. With enough time, resources, and determination, the physics says we can. The real question is, will we? Do we have the vision to commit to a project that spans centuries? Do we have the wisdom to do it responsibly? And do we have the courage to reach for something this impossibly ambitious? Because if we do, Venus might not be hell forever. It might be heaven, a second chance for humanity, floating in the clouds, waiting for us to claim it.